This lesson is going to cover geometric probability when we use probability using lines, polygons, and solids. What is geometric probability? When you're given certain geometric figures, polygons, solids, and lines, we use geometric probability. Usually you have a part of some solid or polygon or whatever that is shaded, painted, or used. And then we need to find the probability of those shaded, painted, or used regions by calculating either length, perimeter, area, or volume, depending on the type of shape that we're given. First, we're going to start with lines. If you're given a line or perimeter L, and you're only looking for a part of it, say A, the probability of randomly choosing an element of A is given by length of A over the length of L. So here's an example. I have given you a number line, A, B, C, D, E, F, so line AF. We randomly choose a point on segment AF. The probability that this point will be located on BC is given by the length of BC over the length of AF. So the length of BC is 5 centimeters, and the total length of AF, 4 plus 5 plus 2 plus 3 plus 3 is 17. So the probability that it will be on BC, or if we choose a point on BC, it'll be 5 over 17. As we continue in this chapter, I don't really mind whether or not you leave your fractions as fractions or decimals or percents, but fractions, whether they are simplified or expanded, and percents are very much encouraged. Another example on lines and perimeter, we randomly choose a point on the sides of a rectangle ABCD, as you see here on the right. The probability that this point will be located on side AD, so here's AD, is given by the length of AD over the perimeter of ABCD. So pretend like this is a fence. And what if I were to throw an apple from the sky? The probability that it lands on this side AD, well, the length of AD is 5, and the perimeter, 8 plus 5 plus 8 plus 5 is 26. So it'll be 5 out of 26. Now let's talk about probability using area. Call a polygon or circle S, and let A be a part of object S. The probability of randomly choosing an element of A is, in this case, the area of A over the area of S. Here's our first example. We randomly choose a point in the square on the right. The probability that this point will be located in the red disk is given by the area of the red disk over the area of the square. So the disk is a circle, so we're going to use pi r squared, where r is 6. And to find the area of the square, you just do 12 times 12. So the probability that it will locate it on the red is 113.04 centimeters squared over the total 144 centimeters squared. A second example, we randomly choose a point in the regular octagon on the right. An octagon is made up of 8 triangles. 2 are shaded here, and 6 are white. The probability that this point will be located in the white region is given by the area of the white region over the area of the octagon. But you'll notice that I don't really have given you any areas, no apothem, no nothing. But you do know what this octagon is made up of. So in this case, the probability that it will be in the white is 6 units squared over the 8 units squared in terms of the triangles that make up this octagon. Now we're going to talk about probability with volume. Call a 3D object solid V with a finite volume. Let A be a part of the object V. The probability of randomly choosing an element of A is given by, now we have volume of A over the volume of B, or in this case it should be B. Here's an example. We randomly choose a point in the right prism on the right, or in the lower right. The probability that this point will be located in the red prism is given by, well, first, you need to find the volume of the red and then the volume of the total prism. So if we look at the volume of the red prism, we have prisms, so length times width times height. So 2 times 8 times 6 gives us 80 centimeters cubed. And the whole volume of the big prism, 8 times 5 times 6 gives us 240 centimeters cubed. So the probability that it will land inside the red prism is 80 over 240. Here's another example. We randomly choose a point in the following regular hexagonal prism. The probability that this point will be located in the red prism is given by, so before we just go on, volume 8 of a prism like this, you know that it is a hexagon. I gave you the apothem. You know the bases are hexagons. You know that the height of the little one is 3.5 and the height of the big one is 12, and each side is 4 centimeters long. If we were to find the volume of the red prism, if we want to find the point, the probability of getting it in the red prism, you would do red, volume of red, over volume of whole. So if I find the volume of the red prism, it's 210 centimeters cubed, and the volume of the big prism is 720 centimeters cubed. So the probability is 210 over 720. And that is the end of geometric probability.